Welcome to this explainer. Today we're diving deep into a high-stakes, kind of mind-bending world where a tiny little change in one pipe can literally cascade into a massive industrial disaster. We're talking about the science of plant-wide control, specifically mastering complete chemical processes.
So, here's our game plan for today. We'll start with the big picture of control, look at systems with interacting units, and then beware the snowball effect. After that, we'll see how surge tanks come to the rescue and finish up by designing plant-wide harmony.
All right, let's jump right into Section 1, the big picture of control, moving from single loops to complete plants.
It's pretty fascinating to realize that managing an entire plant is fundamentally different from just, say, controlling a single machine. Think about modern chemical plants, like massive oil refineries or ethylene plants. They don't just turn on and off like your car. They're running 24 hours a day for 330 days or more every single year. Because of that huge, nonstop scale, manual control is, well, it's literally impossible. Automatic, plant-wide control is absolutely essential. It's really the overarching philosophy that dictates structural decisions to manage all those interconnected systems safely and profitably. So why do we need this massive control architecture? Well, the main goals are actually pretty simple on paper, but man, they are incredibly demanding in practice. We need to increase process yields and drop operational costs. But, and this is crucial, we have to do that without ever sacrificing the safety of the personnel and equipment. Plus, we've got to strictly satisfy environmental standards. It's a constant, highly delicate balancing act.
With those big goals in mind, let's zoom in on Section 2. Systems with interacting units and the multivariable web.
To really grasp plant-wide control, we have to kind of zoom out. A single machine, it might just have one input and one output, a nice, simple, single-loop setup. But real, modern plants, they deal with MIMO. That stands for multi-input, multi-output systems. In a big facility, you've got thousands of process variables, things like compositions, temperatures, and pressures, and they all have to be monitored and adjusted at the exact same time.
Think about a really complex interconnected system. You've got an invisible web of cause and effect everywhere. In a MIMO system, when a controller tweaks a variable to fix one specific problem, like, let's say, cooling down a tank, that very adjustment can accidentally ripple through the process and throw a totally different interconnected unit completely off balance. It's essentially a continuous chain reaction.
And that invisible, interconnected web brings us to Section 3. Beware the snowball effect, where a ripple becomes a tsunami.
Because absolutely everything is connected, treating these process variables is kind of like managing a super precarious line of dominoes. The crucial thing to remember is that an operational disturbance almost never just stays isolated in a plant. It propagates. It travels from one unit to the next, often picking up dangerous momentum along the way.
Engineers actually have a pretty ominous name for this. They call it the snowball effect. Here's how it goes down. Step 1, a seemingly tiny load change happens somewhere in the process. Step 2, that change sneaks into a recycle loop. Now, recycle loops are super common. They feed material back into the system to increase yield. But here's Step 3. Because of that continuous feedback loop, the small change starts multiplying. Suddenly, flow rates are wildly spinning out of control. A minor little hiccup rapidly accelerates into a massive surge.
So this begs the ultimate engineering question. How on earth do we stop this erratic cascade before it blows out a valve, ruins an entire product batch, or causes a catastrophic plant shutdown?
Well, the answer leads us to Section 4, surge tanks to the rescue, the plant's vital shock absorbers.
The simplicity of the solution here is actually pretty brilliant. It's intermediate storage. A surge tank is placed intentionally right between different processing steps. Its whole job, literally its only purpose, is to absorb rapid, erratic changes in inlet streams before they can reach the next sensitive piece of equipment. Think about it exactly like the suspension system on your car. You hit a huge pothole, the shock absorber takes the brunt of the hit, and the chassis stays perfectly smooth.
Now, to use a surge tank properly, it's vital to know the difference between two main control strategies: tight level control and averaging surge control. They are very different approaches. Tight level control fights aggressively to keep the liquid level exact. And that's great if you need a constant residence time, like in a bioreactor. But the downside, it passes any incoming shocks immediately forward down the line. Averaging control, on the other hand, intentionally lets the liquid level rise and fall. It acts as a buffer, damping out those upstream disturbances and smoothly protecting the downstream equipment.
And that is what builds such a brilliant defense against the snowball effect. By purposely letting the tank's liquid level fluctuate up and down, as long as it stays within safe high and low limits, of course, the exit flow rate only has to change very gradually. The tank literally swallows the disturbance. It completely isolates the rest of the plant from that dangerous snowball cascade.
Which brings us to our final stop today, Section 5, Designing Plant-Wide Harmony Using the Systems Approach.
You definitely don't get this kind of harmony by accident. Engineers have to follow a really strict, methodical design roadmap. First, they select the exact manipulated variables, then they decide on the controlled variables, choose any extra measured variables for safety, and finally design the overall control configuration. They're carefully making structural decisions so every single intermediate system aligns perfectly with the one right before it and the one right after it. Now let me tell you, the stakes for getting this roadmap right are incredibly high. In a multi-loop control scheme, if you pair the wrong controlled variable with the wrong manipulated variable, well, the results are pretty disastrous. Get those pairings wrong, and you've inadvertently engineered your own failure. You just threw away your system stability margins, which leads to wild oscillations and poor control performance. It completely defeats the entire purpose of your multi-million-dollar plant.
There's a quote from the source material that sums this up just perfectly. It says, "Even if all the individual components are functioning properly, there is no guarantee that the overall system will perform properly. Thus, a systems approach is required. Having perfect individual state-of-the-art parts, it's totally meaningless if you don't have a holistic systems approach to tie them all together."
Which leaves us with this final thought. Next time you drive past a massive industrial plant, with its miles of pipes and towering columns running silently in the background, ask yourself, what invisible dominoes are falling in there right now? What sudden surges are being expertly caught and quieted by surge tanks, keeping our modern world running safely and profitably? Thanks so much for joining me for this explainer, and keep questioning the complex systems all around you.